Okay. Okay, so we plug in the points for the cosine graph. We plot those. So at 0, we have a point at 1. At pi over 2, it's at 0. At pi, it's at -1. At 3 pi over 2, it's at 0. And at 2 pi, it's back at 1. So basically, we get a curve like this. Okay? So what are the similarities and differences between the sine function? So what about this graph is like the sine function? Jordan? Good. Okay, so it's the same pattern of points, all right? It's even cycling through the same numbers, the specific points that are important to us, hit 0, 1, and -1, okay? So what's different about this than the sine function graph? Jenny? Good. Okay, so the sine function graph started here. The sine function is basically like a shifting of this graph in a certain direction. Okay, so I'm going to show that to you guys on the calculator in a minute as well. The period for the cosine graph, which we know is important because all the horizontal stretches and compressions, they change the period of the graph. So the period of the graph, just like the sine function, it goes through one cycle of all its points by the time you go around the unit circle one time, so in 2 pi. Okay? And then if we have a horizontal stretch or compression, we multiply that by whatever number is there to change it. Okay? The amplitude, so like what is the amplitude right now for the graph? 1. So remember you kind of have this like axis right here running through the middle, and your amplitude is how far above or below that your maximum or your minimum points are, which they are 1 unit. Okay? And again, we can adjust the amplitude by putting some number here in front of the cosine function that then multiplies it by like 3 or 4 or 2, whatever it might be, that stretches it or compresses it vertically. Okay? So we want to know the sine and the cosine function. So cool thing is they're similar. They both look like waves. However, we have to keep them separate by knowing where they start. So the sine function, if you guys remembered, so don't put this on your parent function graph, but I'm just going to put it right here so you can see the difference for those of you that weren't here or you forget. The sine function looked like this. It had a point at 0, 0. At pi over 2, it hit its maximum. Then it was back at 0 at pi. At 3 pi over 2, it hit the minimum. And then it was back at 0 at 2 pi. So this was what the sine function graph looked like. So notice that the shapes are the same type of curve, and they'll both continue in that direction. But for the sine, you have to go from 0, maximum, 0, minimum, and back to 0. For the cosine, you're going to start at the maximum and then cycle through the same points. Okay? Are we all right with this idea? All right, so we want to just do to the cosine graph all the same things that we did to the sine function graph. Okay? So we want to go through. So first we just want to graph this. So y equals 1/2 the cosine of theta. And we want to say what the period is and what the amplitude is. Okay? And we decided after walking through one of the examples last time that when we look at the period, we would want to do that calculation first, because knowing what the period is helps us scale our graph appropriately. Okay? So what is going to be the period for this function? We were going to graph y equals 1/2 cosine of x. So what's the normal period for the cosine function? 2 pi. Okay. Is there anything in this function that's affecting the period? What kind of transformation affects the period of the graph? Horizontal stretches or compressions. Is there any number in the spot that would cause a horizontal stretch or compression for this function? Okay? So that would be a number inside the cosine function multiplying the variable right here. We don't have a 2 theta or a 1/2 theta, so we don't have that happening here. Okay? So that means our period is unaffected. Okay? That it's going to be 2 pi. Yep. That's going to affect the amplitude. So that's going to be vertically how high the maximums and minimums are stretched. Okay? So here, what it means when we know that our period is 2 pi is that as we go through the points of the cosine function, and again, you have to remember the cosine parent function starts there, okay? And then it goes like this. Right? That's the pattern of points that we saw. Okay. So remember, I can fill this pattern of points in on my graph without labeling anything, and then I can say, well, since I know the period is 2 pi, I'm going to make that last point once I've completed the stage 2 pi, and then I'm going to go scale the rest of the graph. So this is what we had talked about yesterday. Okay. So if that's 2 pi, I can either cut that by 4, divide it by 4 to figure out what's right here, or if that's confusing, I can take it and split it in half. So what's 2 pi divided by 2? Pi. So halfway between there would be pi. But then I need this other mark that's halfway between that. So if I take pi and split it in half, I would get pi over 2. So this graph is going to be best served scaling it by pi over 2. So then we talked about if you struggle with fractions, don't be like, oh, now I can't scale it because I don't know how. Just count them. So like 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and if you wanted to keep going, then we would just go 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2, and you could keep going in either direction. Okay? All right, so this is what the parent function would look like. Okay? And it's just kind of the most basic parent function because we didn't have a horizontal stretch or compression affecting our scale. So then we want to do any other transformations that are here. There are no other horizontal transformations. There's no reflections. There's no translations or shifts left or right. Okay. The only other transformation in this problem is the 1/2. Okay. And what is the 1/2? What kind of transformation is that? So think, is it horizontal or vertical first? Vertical. Okay. Is it a shift, like it's going to pick the whole graph up and move it? Or is it a stretch and compression, or is it a reflection? It's a stretch or compression, and in this case, it's a compression, right? So it takes where our normal maximums and minimums were and changes them to half the distance or multiplies that distance by half. Essentially, that number affects our amplitude. So that's kind of easy to remember that like our A value affects our amplitude. So now instead of being 1, our amplitude is going to be 1/2. So how our final graph is going to look, this axis is not getting shifted at all because we're not moving anything up or down. All that's changing is the amplitude. So these points are going to stay. So we're not moving the graph. But these points that were our maximums or were our minimums and they were 1 unit away are now only going to be half a unit away because our amplitude is 1/2. So this maximum is only going to be at half a unit above the axis. This minimum is only going to be at half a unit below the axis. This maximum is only going to be at half a unit above the axis. And you can see the adjustment in the curve. And then we could continue the pattern if we wanted to see the graph further out in either direction. Okay? Is this okay with everybody? Yes? All right, so then we're going to do one that's harder, and then we're going to let you guys start the homework. And then the homework is going to have a mix of some cosine and some sine problems on it, so you can practice starting with the appropriate parent function. Okay? Any questions on this before we try one with multiple transformations? Okay. All right, so here's what we're going to graph. No, this wasn't in your packet. Sorry. Okay. All right, so the first thing I want you to do before we graph this, so this is separate from any of the ones in your packet because I want you to see something that has a little bit more transformations in it because I think it then makes the ones that only have 1 or 2 transformations in them simpler for you to do after we've done some more difficult ones. So first thing I want you to do is we would rewrite this. Just to factor the -3 out. And what would be in parentheses with the x here? So this would be -3 times x, so pi over 3, okay, plus or a minus in here? Plus, because we factored out the negative. All right. Now, what I want you guys to do, if you're unsure, you can work with the person next to you. But before we start graphing this, I want you guys to do the following. I want you to list all the transformations, so you know what we're going to have to do to the parent function. Okay? And then I also want you to determine the period and the amplitude of the graph. Okay? So I'm not asking you to graph anything yet. If you're ahead of yourself and that's not a problem for you, then you can go ahead and graph it. But I'm asking you to look at the function, figure out the period, figure out the amplitude, and list everything that has to happen. Okay? What kind of reflections, what kind of stretches, compressions, all that kind of stuff. Does that make sense? So first just do all that stuff so we know what's going on, and then we'll work on putting it on the graph. Okay? So take a... Okay. So first thing I need to know from somebody. So stop your discussions at this point. Okay, first thing you'd want to put on your graph is the scale. So that's why after not asking you to graph anything, I asked you to think about that. And the scale's totally going to be based on what you calculated the period as. So what did you guys get for the period of the graph? 2 pi over 3. So for those of you that are struggling, where that's coming from, 2 pi is the normal period of the graph. Okay? The period is only affected by horizontal stretches and compressions. So we know that having a 3 here really means that horizontally we're multiplying distances by 1/3. That's a horizontal compression. So that's exactly what we're going to do to our period is we're going to multiply it by 1/3. And we're going to get 2 pi over 3 as our period. Okay? So what that means for me is that my cosine parent function that normally goes in this order of points right here, I want this cycle of the graph to happen in one period, which means I want it to end at 2 pi over 3. Notice that I didn't make it look any different than when it ended at 2 pi. I'm just changing the numbers on the scale to make my life easier. Okay? So I want that last number to be 2 pi over 3. So I need to know how to label my graph. Okay? So how am I going to label my graph? What is this going to be my scale by? So I have a couple of options. I can take this and divide it by 4, and that will give me what this number is right here. Okay? If that doesn't make sense to you, you could take this and divide it by 2 to get what's right here, and then divide it by 2 again. So 2 pi over 3 divided by 2, what would that be? Times it by a half if you're not sure. So what's 2 pi over 3 times a half? Yeah. Okay? So that means halfway between the beginning and 2 pi over 3 is pi over 3. Okay? Because I got to get what this is. If I don't have what this scale is, I can't number my entire graph. So like if somebody doesn't scale the graph for you, normally you number it by 1s, right? But then if numbers get really big or something, you might number it by 2s or 3s, but you indicate that on the graph. That's what needs to happen here. Okay? So the minute that you know that you want the period to end here, half of that is what should be in the middle right here, and half of that is what should be this first tick mark right here. So what is half of pi over 3? And again, if you don't know the answer to that question, you just need to write out on your paper pi over 3 times a half, and that's going to give you half of pi over 3, which is going to be pi over 6. Okay, now what that means for me is my graph is going to be scaled by 6ths. Okay? So 1/6, 2/6, 3/6, 4/6. So 3/6 was here, and 3/6 reduces to that. 4/6, 5/6, 6/6, and I could keep going, right? So this is my parent function graph right here. And I already took care of the horizontal compression. So that should have been one of your transformations listed. I took care of it by just naming these appropriately so that the amount of space taken up is less or more by how the axis is scaled. All right, what else happens here? We have this. What is the negative going to do? Horizontally reflect it, which means everything's going to be on the opposite side. So I'm actually going to extend this here. Okay. I'm going to have negative pi over 6. I'm just going to kind of make a mirror image of my axis. negative pi over 3, negative pi over 2, negative 2 pi over 3, negative 5 pi over 6. I'm running out of space, but hopefully you guys have more on your paper. All right? Then I'm going to reflect all of those points. Okay? So this one's on the axis, so it's already right here. But this point at pi over 6 is now going to show up here at negative pi over 6. The one at pi over 3 is going to show up at negative pi over 3, pi over 2, 3 pi over 2. Okay? So I have the reflection of my cosine graph horizontally. Okay? So scaling the graph took care of this transformation. I just reflected it, so I've taken care of that transformation. What other horizontal change has to take place? What is this? It's going to move to the left. And how much? How much is it going to move to the left? Pi over 3. Now, we got to be careful. Was our graph scaled by pi over 3? No, it was scaled by what? Pi over 6. How many marks, then, does it take to move over pi over 3? 2 marks is the same as pi over 3. So if that helps you, translate it to number of marks you need to move over in your head and move over that many marks. So I got to make myself one more mark here because I'm not far enough. But so 2 marks that way, 2 marks that way, 2 marks this way, 2 marks this way, 2 marks this way. Okay, sorry, mine's extra ugly because I'm running out of room. Okay, so then I've done this. Right, all the same stuff we've done before, but kind of a worsely scaled axis, something we don't like as much and we have to get used to. Right, and this constant wave thing going on. Now we have to take care of these 2 transformations. Okay, so somebody explain to me how those are going to affect the look of my graph. Okay, so Skylar says like longer, like the maximums and minimums are going to be stretched out more from where the middle is, right? Okay, that's because this 2 right here is going to change the amplitude. And what else about the graph? What's the 1 going to do right here? Move everything up 1. So, sorry. My thing is not calibrated right. I don't know. All right, so I'm going to move it up 1 and change the amplitude to 2. So if you want, you can kind of make yourself a little axis. I find this helpful in graphing it. It's nice for me to have that reference point, like this is now going to be the middle of my graph, so that then I could do the stretches I need to do. I now need an amplitude of 2, so I need my graph to reach 2 units above. So these points that were here, they're going to be the points on the axis. The maximums are still going to be maximums, so they're going to be above the axis, but the amplitude is 2. So instead of reaching just 1 unit above the axis, they should reach 2 units above the axis. So there, and this one should be up there as well. And this guy's still going to be a minimum, but instead of 1 unit below the axis, it should be 2 units below the axis, but the axis is now here, okay? So 2 units below, it actually ends up in the same place. Do you guys get that? Because we moved it up and then stretched it down, okay? So it still ends up here, and then we have our little wave. Okay, and then we could keep going, okay, further to the left or further to the right. Are we okay with this? So take a look at it and ask some questions if you